Okay, so let's continue our review on engine electrical devices. We're going to talk about wiring, circuit breakers, your protection devices, switches, and that sort of thing. This is going to overview. We'll tailor it to the engine, so you won't see a whole lot of not a whole lot of digital logic and that kind of thing. It's mostly going to be like lugging cables and that sort of thing. It's not that the engine doesn't have a lot of digital logic, a lot of advanced avionics. That's totally untrue. That there's a lot of it that's down, and it's becoming more so. It's just that in the engine, that's generally where you're going to find your heavier cables and that sort of thing. We'll also talk about how to fabricate cables, and we'll eventually get into the procedure for choosing the right wire gauge and that sort of thing.
All right, some examples of power plant electrical cables you get. You get one of these, which is a multi-conductor cable. It's just two or more separately insulated conductors in the same jacket. All right, the next one is a twisted pair. It's very, very common in aviation, especially when it comes to any kind of signal wire. All it is you'll have a shielded jacket, or typically you'll have a shielded jacket. You can also not have a shielded jacket and just be just the insulator on there. And then two wires that go on the inside and they twist together. These are very, like I said, very common for avionics, for signals, things like that. In the context of inside the engine, nowadays you're getting a lot of um, engine monitoring systems of a wide variety. They go to a lot of different sensors on the engine. The twisted pair is a common wire that will be used for those sensors. Um, you can also have other types, but like I said, the twisted pair is probably the most common. Now, when we say shielded cables, like the one on the far right, it just has a shield on it. Now, that shield can be underneath the insulation, or it can be over it, either or. Many times, that shield is going to go to a ground pin on the connector or on the back side of the connector, and it'll ground to the aircraft that way. Either way, it's imperative that those grounds are continuous. They can't be broken, or else you'll effectively, what will end up happening is you'll turn this wire into an antenna, and you'll get a bunch of electrical noise and problems with that. I've seen that happen multiple times. So don't ever discount the shield, especially if we end up dealing with coax. You generally coax is generally going to be in a it's a radio frequency cable. It's going to go to antennas and that sort of thing. You generally speaking won't see that on the engine, but you may. Either way, the coax, you'll have a single strand wire in the middle, and then you'll have a dielectric that goes around it, and then you have shielding that goes on top of that. The single strand and that shielding can't touch, and if they do, and this typically happens during terminations when they're installing new wires, if they do, then that will cause a problem, and so you don't want to do that. You can also have quadrax, which is four strand wires in the middle. Triax, three strand wires in the middle. I'm not aware of a duax or a two wire coax, but I don't see why you couldn't have that happen. So either way, they would all be separated with their own dielectric material, and they would be shielded in the same way. But those are the types of wires that we could potentially. Okay, the wire sizes are always going to be done in gauges, per the American wire gauge, and this is a sample set of information about the American wire gauge. You can see the gauge numbers off on the left, and all the information about the wires to your right. So your gauges at the largest will be a 4/0, then it'll go 3/0, 2/0, all the way down into a 2 gauge wire, 3 gauge wire, 4 gauge wire. And it gets smaller as the gauge number goes up. Mostly on your avionics stuff, you're going to get anywhere between I think it's as big as a 14 gauge wire. Typically, you're going to see like 16s to 24, somewhere in that. You get like 16, 22, 14. You'll see some 18s every once in a while. For heavier gauge wires, for like your battery cables, starter cables, and stuff like that. It has to carry a lot of current. You're going to get smaller than that, but these are few and far between. There's only a handful of them that are on there, and they may be up to anywhere between 4 to 9 or so, just depending on the load that ends up it has to carry in the aircraft that it's on. You can also see on there the ohms per 1,000 feet. The temperature also has an effect on it, and all that. So the main thing is that like you want to make sure that you get the right gauge wire for your application. And we're going to get into here in a little bit, like how to select that if it's not clearly annotated on some sort of engineering document that that you're working with. But the reason being is that like you can see the wild difference between a 4-aught wire at 77 degrees down to a 30 gauge wire at 77 degrees, and the difference in the what how much resistance it offers for any current going on. So that is the American wire gauge. All right, so one of the best things about wire gauges or wires on aircraft is that you can identify them pretty easily. So every 6 feet, they'll have a stamp on there that will tell you what wire what wire it is. They will have some sort of naming convention. Typically, the last two numbers is going to be the gauge of the wire. Then typically the preceding 2 to 3 digits plus whatever the alphanumeric is will correspond to an ATA chapter plus whatever device it is plus whatever subcomponent of that device is. So now that's not ubiquitous. It's not going to happen across the board with everyone, but it will. But it does happen. There's always some sort of naming convention of some variety for wires with wire numbers printed on there, and those will also correspond to your wiring diagram. So if you break open a panel and you're looking for a certain wire, this is how you go about finding it. You can start looking at the numbers on the end. You say, like, hey, look, I know it's a 20 gauge wire, it's a small wire, or maybe it's a 2 gauge wire, it's a big wire, and then you can immediately kind of cut down the wires you're looking at right then and there just by size alone. Then like you get like all the small wires and you're like, okay, I know it's coming from on this example it's Hotel 215 Alpha. All right, so if I know that 215 goes to the I don't know, landing gear, then I can say like, oh, well, this is all coming out of the landing gear. Well, that small wire is probably this subset of small wires right here, and I can start to kind of like pick it apart until I find the right one that I'm looking for. That is, and like that's kind of like a rough way that you can go about finding it quickly. Now on small GA airplanes, you may not have this, especially if they're older. This was something that came around probably like the mid 70s or so, and started becoming like a more and more common thing with newer and newer aircraft. On heavy commercial aviation, any Boeing, any Airbus platform is going to have this on there. Any Embraer platform is going to have this sort of convention. They're all slightly different, just a little bit, because there's not a standardized way of like you have to do it this way. The most common is the most common standard you'll have is the last two digits. There's always going to be the wire or the wire gauge, but everything else may have some variation to it. So once you kind of learn one manufacturer, it becomes very easy to start picking up on where they're going. But this is how you can find it pretty quickly. And I would encourage you to always like look for wire numbers and then make sure that you have the wiring diagram that you're hunting for like in your hand, so that way you can find it quickly. All right, here's a few examples of what it could potentially look like. You can see on this terminal block here, you have a bolt that's holding two wires together. And you'll see that H215 Bravo 20 is there at the top. So 20 is going to be the wire gauge. H215 is the application, but there's a Bravo side and an Alpha side on it. And then underneath it, it goes 215 to 216, 217, 218. And so you can very easily start to see where they go and what side they're on, and you can start to infer little things like that. Now, this is for a make-believe manufacturer, so obviously, like there is no terminal block 1. You can see there the terminal block there at the very bottom with these particular wire numbers going there. but you get the concept. So everybody's going to be a little bit different. And once you've kind of learned one, then it becomes very easily to jump to the next one and the next one and the next one because you kind of see what they're doing, and it becomes pretty easy to navigate. All right. This is another way that you can potentially see it done. You can see tape with the bundle number on it. You can also see a sleeve marker that's basically it's tied on. That's the kind of the old school way they do it. If you go to the Lear, you pop open the nose, you'll see that there a sleeve marker in there that has hey look, this goes to the landing gear or whatever, or maybe a wire bundle number. The older the aircraft, the more kind of chaotic the wiring identification gets, because this was something that it took aviation time to kind of develop and standardize across the board. Nowadays, it's fairly well standard. Even for small GA planes, you can order wire individual wires with the number printed on it, and you can get it customized. So as time goes on, more and more people are starting to do things the standardized way. However, the older aircraft are still a little bit chaotic. You'll see some of this stuff on there. There's also the element of exposure to the elements, especially like in the landing gear and stuff like that. Sometimes they will put these tags on there, and they'll get SkyDraw on them, whatever, and they'll fall off. So no, this is like these. This is not the most reliable way to do it. The stamping on there is fairly reliable. You can take some isopropyl alcohol, clean the wire up, and generally speaking, you won't remove the marker or the stamping or whatever that is on the wire insulation itself. Now, when it comes to installing wires, there's another thing that you should be aware of. A lot of times, these wire bundles will get they'll come off their independent devices. Say it's all off of the flaps when any of their servos that are running the flaps and the wings. They all the flap wires come together. But they have to come and they have to go down the wing. They have to go through a pass through into the fuselage to eventually get up to the eBay cockpit or wherever. Well, they're right beside another wire bundle for, say, the fuel cell or whatever. And so what will end up happening is that they end up getting grouped together. Now, sometimes they end up getting staggered or stacked on top of each other, but if they end up getting grouped together, you could end up having individual group ties in the entire wire bundle itself. And so you'd have like a bundle that is mixing with another bundle, and those two bundles become one big bundle, but there's still group ties that go down the length of that wire run, so that way you can easily access just the flap wires if that's the case that you need, or maybe just the fuel cell wires, rather than having to break open the entire bundle and sort through a gazillion wires. You already cut it in half just because you know that the group tie is correct, and that'll happen every 6 feet, depending on what standard that's being worked to and what the engineering says. But generally speaking, you'll have wire ties at least every 6 feet, if not every 2 to 3 feet in there. And then so what you would want to do is that if your bundles are getting tied together every 3 feet, then your group, what you want to do is, like, if you tie, let's say you have like a 10-foot wire run. You do your first tie for your bundle at foot number 1. Your next tie for your bundle at foot number 3. Then what you want to do is do your group tie at foot 2, and then at 4, and so on and so forth. So that way they're staggered across the whole thing. Now, generally speaking, you won't have to do that. What will end up happening is that those groups will be tied together in individual runs, and what you're doing is you're putting those two wire bundles together and then tying it up. Now, more common than not, especially if it's on a bigger plane that's got space, they will be stacked one on top of the other and separated from each other. Especially Airbus planes are very good about doing this. Boeing's a little bit different, just because they kind of like invented the whole process, and they just are doing the way that they did it way back when. Airbus has kind of come along, learned from Boeing, and try to improve on the process. Generally speaking, when it comes to wiring, at least. And so you'll start to see them get stacked up that way. Small GA airplanes. This is also pretty common, actually. Whenever you open up a panel and you look behind it, the old way of doing stuff was just to smash all the wires together and to make this like big rat's nest of confusion. Whereas the avionics shops nowadays are getting better and better about making independent runs, so that way you can easily troubleshoot and access and all that good stuff. But just know that that's another way to that you may end up identifying wires just by simply what bundle it's in, and a lot of times those bundles will be labeled. Okay, here's another one. This one I'm pretty passionate about actually. Is staggering your splices. Now, a lot of times, what will end up happening is that you'll end up having to splice a wire run. Yeah, for whatever any number of reasons, damage, it doesn't matter. All right. Instead, the temptation becomes to basically cut the one wire bundle off, just straight off in one spot, and then take the adjoining one and then just start putting splices together. That is the way wrong answer, because what will end up happening is that like you'll peanut butter tape over the top of it and try to like protect the splices, and what will end up you'll have this big ball in the middle of this wire run that makes like a number of things more difficult. So the best way to do it is to go take the we'll call it bundle A and bundle B. Bundle A is going to lay into bundle B. You take the longest wire from bundle A, lay it into bundle B, cut bundle B's wire at wherever that bundle A wire lands, and then splice right there. Then you take the next wire from bundle A, and then you trim off 2 or 3 inches, and you lay it over into bundle B, and you repeat the process. And you keep doing that, and as you do that, it will stagger the splices out. Now, and whenever you do a splice, you'll end up having to label it, and then put it into the maintenance log in whatever way they're capturing maintenance log on that particular airplane. And keep in mind, you're only allowed 2 splices per wire run. Now, that could change based on the maintenance manual you're working with, engineering that you're working with, all that good stuff. But generally speaking, you don't want to have more than 2 splices in a wire, and if you do, you just want to replace the wire. A splice a splice, with the exception of the ones that are designed by engineering and placed in the wiring diagram and meant to be there, is basically just a band-aid. Instead of trying to save everybody time and money, instead of replacing this one long wire that might go from nose cone to tail cone, instead you can just simply just put one splice in there, and that's all there is to it. But what you don't want to have happen is one wire that has a gazillion splices in it, because splices will even environmental splices that are done correctly and stuff, they'll break down over time, they'll corrode, they'll have problems, and so you don't want to try to keep putting splices into this wire, because you're just inducing thousands of more possibilities of failure happening, and then just future work in the process. All right, so another thing that you want to do is whenever you go to do a wire installation, you do not want to do what's called banjoing the wire. You don't want to make it super duper tight. You want to have some slack. Now, this has got on there that they want to have a 1/2 inch deflection with normal hand pressure between 2 Adele clamps. That's a good rule, good rule as any. There's a certain amount of just experience that comes with this. You don't want it to be sloppy and slacky, so it just falls all over the place, because that's just going to lead to chafing. It's just bad work. However, you don't want to make it super duper tight either. The 8083 says you want it to be able to have that slack for easy maintenance, allow for replacement of terminals, relieve mechanical strain on the wires, permit free movement of shock vibration, and permit shifting of equipment for purposes of maintenance. I would say, you definitely don't want it to be super duper tight, so that way you can't work around it. But really, you shouldn't be manipulating wire bundles that much whenever you're doing maintenance anyways. But neither here nor there. You don't if you put it in there super tight, what you effectively do is you induce stress and strain into the wire that will cut into that will then cut into anything that it can. So if that Adele clamp wears through the rubber rubber grommet, and it falls through, or gets cut or whatever, dry rots, and then it attaches to the metal. If it's slack, it will sit there, and you have a lot more time to catch that fault before it actually starts to cut into the wire. If it's super, super tight, what it's going to do is then it's going to bear down on that metal edge, and it'll cut through it a lot faster. So generally speaking, you don't want to have a whole lot of slack in the wires if you can help it, or a whole lot. You don't want to have a whole lot of slack, and you don't want it to be super duper tight. You want it to have just enough where you can grab it, kind of move it a little bit, and that's it. Okay, when we're routing wires, we want to be cognizant of a couple things. We want to make sure that that does not chafe first and foremost. Don't let it rub on anything or else it'll cut itself off. Try to stay away from high temperatures, so especially around power plants. You've got to think about where that exhaust is at, where the bleed air is at, if there's anything electrical that could potentially get hot, and what that will do to the wire, because it will basically, even you don't even have to be exposed to flame. Just heat itself will cause the insulation to start to break down. It causes the resistance of the wire to drop, and therefore the current goes up. The current goes up, you start getting more heat, and you could end up in a bad situation there, or it'll just burn up. You also want to make sure that it's nowhere where it's going to be used as a handhold or support for any sort of like personal belongings or equipment. So try to route them in places that it's inconvenient for you to touch. And that will keep them safe from people just coming and going. Damage by personnel from moving within the aircraft. So most of the time, this is going to be protected by structure. It's going to be routed underneath places or inside of walls or things like that. Damage from cargo stowage or shifting. Now, once again, it's kind of the same thing. Damage from battery acid fume spray or spillage is something you need to be cognizant of, especially on your GA airplanes. Just stay away from batteries if at all possible. Especially if it's a lithium ion battery or it's a sealed battery, which most batteries these days are kind of getting to where they're all sealed. You don't have nearly the concern. But if it's the old lead acid batteries, they could potentially boil and bubble over. That battery acid will eat through everything and anything. And a wire really structurally just doesn't have a whole lot to it. It's basically a bit of copper, a bit of aluminum, and some plastic wrapped around it. So that battery acid will do a number on it. The last one, probably the biggest one, is solvents and fluids. Now, this is a big deal in landing gear of heavy commercial airplanes. In the landing gear on the wheel well, I've never seen one that's not like caked with Skydraw and debris and stuff like that. At least on the 737, some of the bigger planes they're a little bit better. But either way, it's just a naturally dirty area, and there's always like some sort of leak, and that will always get on there. So after TWA Flight 800 blew up, they started what's a program called they know as EWIS, is Electrical Wire Interconnect System Maintenance. And so you'll get EWIS checks and inspections on a lot of these wires, and that basically means that you take a bristle brush and a squirt bottle full of isopropyl alcohol, and you go clean out the wire bundles and try to get all the dirt and junk and solvents and fluids off of them, because they will eat through those wires, and then they will start to cause problems, especially if it gets any sort of place that's chafed or whatever. It just starts this whole menagerie of problems in that spot. So try to get it in a way. Think about like where the fluid could potentially come from, where it's going to go, which way gravity's going, which way is the wind blowing. Is the wind going to blow it into the wire bundle? And try to route it that way. Okay, so kind of continue on our chafing conversation. This is some things to think through whenever you're talking about routing a wire through a lighting hole or whatever. They should have a Adele clamp standoff that's tied off to a bracket there. You should have an approved grommet around the hole, so in case the wire does touch the metal, it's not touching the actual metal; it's just touching the rubber of the grommet. And the wires should be less than a quarter inch from the hole edge. So they should have plenty of clearance, so that way it can get through the lighting hole without any problem. And this goes for any other type of routing that you may come across. Is that you generally want to use clamps. Clamps are great. They're a pain to get on and off. I will be the first to admit that. However, in terms of just keeping the wire safe, it's much better for that. Okay, so let's now talk about wire bundles and putting them together. We're not going to go over this super in depth. You should have covered it in airframe. Nothing has really changed. The one thing I will remind you is to put a clove hitch as the knot. If you get this on your OMPs or you get out in the wide world and you forget, it's always in AC 4313. But clove hitch is the knot that you want. All right, when stripping wires, you're going to use wire strippers. You're not going to use a pocket knife or razor blades or anything like that. You're going to use the actual hand strippers that we have here, or that you should have available to you as an aircraft maintenance technician. You're going to put the wire in the appropriate slot, as you see on figure 1 right there. You're going to hold the wire, don't let the wire move, and you're going to squeeze the strippers. That will then shear the outer insulation, and then pull the insulation off, and you have a nice clean wire strip right there. Don't move the wire around. Make sure you have it in the right slot. If you put it in a slot that's too small, it will damage the wires on the inside. Now, it may not seem like a big deal, but there's been many cases where you start getting intermittent faults because of corrosion being induced because somebody used the wire strippers incorrectly, or they decided to use a pocket knife or a razor blade or something like that. Aviation's a game of aim small, miss small, and this is definitely one of those things where you need to have a high attention to detail, because if you don't, the problem won't manifest with you. You'll think you did a good job. But a couple of years down the road, it'll start to show up, and so we don't want to do that. All right, the vast majority of your wire installations on the power plant side are actually not going to be like small, like 14, 16, 22, 22 gauge wires. They're actually going to be much heavier terminal lugs, going to like starters and batteries and that sort of thing. Now, you have your ECUs and things like that on more modern GA aircraft. But whenever you're thinking about like kind of your stereotypical certified airplanes in the power plant section, for the most part, your wires are generally going to be a little bit heavier because you're closer to the battery. It's carrying a lot of weight, higher amperage, and all that jazz. And so whenever you're actually putting your large lugs on to install to a heavier wire, this is the process you're gonna go through. You're going to take your terminal lug. You'll put some. This has petroleum, which is just basically KY jelly, but any sort of electrical lubricant will work. And the idea is that you're gonna make your life easier and have a better connection because it's conductive. So you'll slide that terminal lug over the wire. Now notice on this in the bottom left hand corner where it says stripped wire, that lug has a shoulder on it. That shoulder is meant to go over the installation, and so that way the exposed wire, your stripped wire, is covered totally inside of the little terminal lug right there. Then you're going to you'll put it in the lugger, crimp down on it. Make sure you watch your finger, because once the lugger clicks, the only way to get it to open back up is to go all the way down and come back up. And that can be absurdly painful. If you pinch your finger in there, the only way to get it out is to continue all the way down. So it's just going to get worse before it gets better. Now, one of the things I want to point out here is like where they have this little pencil pointing there. Your wires should not come out beyond the lug. They should be sitting in there. However, they should be as close to the end as possible. And so if you did your measuring right whenever you put it in the stripper, then that should be pretty close. At Boeing, they would actually have us take a 6-inch scale and then and measure it all out, so that way it was super precise whenever we strip the wires. I don't think that's 100% necessary. You can get pretty close just by eyeballing it, but whenever you're first starting out, a scale would probably be advisable, because it's going to take you probably doing it 100 times before you can get to where you just eyeball it and put it on there and off you go. Okay, so I will say this: there's a lot of information in the wiring chapter in the 8883 that's pretty niche. You probably won't ever see the vast majority of them. However, this one is one I do think is warranted to pay a lot of attention to. Terminal blocks are a place where it's very, very easy to induce electrical faults and start fires, because, and you can see, especially on your higher amperage terminal blocks, you have these connectors that are by nature going to be are going to be exposed, and it's very easy for something to get on them and cause a short, or for them to touch each other. I've seen more than one fire start because of a high amperage terminal block where something was either dropped on it or leaked on it, or somebody installed something incorrectly. So I wanted to point this out on this terminal block in particular, and it's pretty common. There's going to be these non-conductive posts, like a little plastic post. Notice how they have the terminal block pulled all the way over, so that way it touches that non-conductive post. If you whenever you go to install them, you're going to put them on there, go all the way to the right, so that way it touches that, and then you'll torque your bolt down. Now, as once the torque hits its inflection point, it's going to want to grab that lug and want to turn it. And it should be turning. It'll turn it away because you're tightening it down. It's going to want to turn away from that post. But you're going to have to hold your finger on that post as you're tightening down the lug. But it should stay. It should stay right there on that non-conductive post, so that way it doesn't spin off and go somewhere else. If you do every single one of them that way, you will create enough space so that way there's a very low chance something gets in between the two of them. And usually they have protective covers on them and all that jazz. But this is something that you want to do, pay a lot of attention to on bus bars, terminal blocks, and that sort of things, because they are a place where faults can get induced fairly easily, and without a whole lot of effort. Okay, another really common fault point for the power plant electrical system is going to be connectors. Be it, common faults are there's a pushed pin in the connector, so at some point, whenever someone installed it, it pushed the pin, like the collets broke and it came back, or maybe they didn't install it correctly, and it's starting to get pushed back. Now because of that. You can get broken contacts off in there. Vibration, especially in the engine, vibration is a pretty serious killer of a lot of different things. And if it wasn't installed 100% correctly over time, the vibration can basically break the contact off from the wire, so you can have faults that way. Corrosion's another big one, probably the most common one for electrical faults in there. But like your connectors, there's endless amount of things that you can say about connectors. You want to make sure that they're installed correct, or they're manufactured correctly. For one, always pull check all your pins. Make sure that you strip them correctly, crimp them correctly, and you seat them in the connector correctly, or else you're going to end up paying for it in the long run. Then make sure that whenever you install it, you line up the keyways first, slide the connector on, and then start screwing it down to secure it. Don't just like start doing the whole let's put two things together and twist it until it just slides into place. That's just going to mess up pins at the end of the day, or induce little bits of FOD into the connection, and you would be surprised how just a little bit can really make for a bad day. I do want to go over this graphic with you. It is pretty neat. So this is the breakdown of an AN connector. So you notice that AN is the standard, so that's the Army Navy standard, and the type, the 3106, is a straight plug. Then the class of plug is an alpha class plug. Size is 1/16. The contact arrangement number, so that means that there's four contacts on there. You can see them there off to the left, A, B, C, and D, which is pretty common for this would be like a firewall pass-through plug for power contact style, and then the insert rotation. So you can get different rotations in different areas. Almost all of them are going to be ones. I can't think of a time that I encountered a left hand rotation, but whatever. But that is how you read a connector plug, or a connector part number. That's helpful, especially whenever you have a big plane with a lot of connectors on there, and you're trying to see if there's something you can borrow from, or whatever, somewhere else, and so maybe some other parts bin, or whatever. This could potentially be helpful to you, as with any part number. The more that you can read some of these part numbers and stuff, the more dangerous you become. Okay, so just a little bit on wire protection devices. So wire protection devices are going to be like your fuses, fuse blocks, circuit breakers, that sort of thing. Anything that protects the engine from or your power plant, whatever your appliance is, from from a high amperage condition. So if something gets grounded out, the amperage goes through the roof. The circuit breaker will pop to keep it from starting a fire, blowing stuff up, or both. This is a wire and circuit protector table. So you have a wire gauge on the left hand side and the fuse amperage on the right hand side, and the circuit breaker amperage in the middle. You notice that the circuit breaker can handle just a little bit more than the fuse will. The fuse will blow way before. The good part about circuit breakers is they're resettable. So if there's some sort of weirdo, wacko thing, kind of one-off that happens, maybe somebody drops something on a terminal block and it shorts it out, the circuit breaker will pop. You can simply just take the thing that got dropped off and then reset the circuit breaker and everything's fine. If you blow a fuse, then you have to replace a fuse. That's the kind of the biggest advantage over circuit breakers over fuses.
Okay, let's say you had to fabricate a starter cable, or you found some sort of wire that was chafed. How do you know what wire you're supposed to choose to replace the wire that you're replacing? Now, this is to satisfy the FAA's requirement. You can do it this way. You can buy just rough wire and get it installed, or get it sent to you in a bundle and then cut it. Lug it out or term it out and install it. Generally speaking, though, especially on heavy commercial aviation, you're never going to do that. What you're going to do is you're going to order a part number, and you're going to get a wire harness that has like everything that you need on it. And you'll take the old one off and put the new one on. The only time that you're ever going to be selecting wire is if you're doing aircraft modifications and it's not clearly defined. Like we're working on a Glacier right now on the hangar floor, and there's a bunch of it'll say like fabricate this wire harness or whatever, and so we have to select the wire for it based on Garmin's instructions, and it makes it fairly clear. So just kind of take this, I would say, with a grain of salt, but like understand that the real world is basically working off of part numbers, not necessarily you just trying to like read some crazy graph and then go out and buy the right wire and fab it up, even though you can do that, and that does happen.
Okay, so let's talk about wire construction. There's a couple of different materials that you could select: is silver, copper, and aluminum. Silver you're probably never going to see because it's super duper expensive, but it is out there. Copper you will see. It's got higher conductivity than aluminum, so it's more preferable to aluminum, but it's more expensive. So that's the trade off there. Aluminum, on the other hand, it's 60% as conductive as copper. It's lightweight. The larger diameter reduces the corona discharge, so electricity loss at higher potential, and it's got a greater radiating surface than copper for conductance bus bars. So therefore, aluminum is by far probably the most common material that you'll see in wiring. Now, there's also a consideration of voltage drop in aircraft wiring. So your main power cables, like your generator to battery bus, the voltage drop will be less than or equal to 2% of our rated voltage at a rated current of or a 5-minute battery discharge rate. Okay, so now we have that out of the way. Let's talk about like how do we go about actually selecting the wire. We know all the engineering specs of the types of wire that we could use. Which one of those types are we going to actually decide? The first thing we're going to we're going to make sure that we prevent excessive voltage drop for a required current over distance, meaning that we need to select the right wire for the right job, so that way we don't drop the voltage, even though it's connected, and all of a sudden the lamp doesn't come on. It's because we chose a wire that is going to shed tons of voltage, and basically it's become a big resistor rather than the appropriate wire for what we're using. We also want to prevent overheating while carrying the required current. So this is a common thing. Voltage drop very rarely is going to be a systemic problem or effect that you see. You will see voltage drop problems because of faults that are in the wire, but you won't see one just because of the wrong wire is selected. However, whenever you see repair work that's not necessarily following any sort of engineering guidelines, any kind of specifications, or anything else like that, you will see people install too small of a wire for too big of a load, and what will end up happening is it will get hot, and it will either melt the insulation on it, it'll discolor it, or the things around it, or it will straight up just start a fire, and so that happens. So we want to prevent those two things, and the way that we prevent those two things is by selecting the correct wire for the correct job. So factors for selection: one is the conductor length, two is the current that's going to carry, three is the permissible voltage drop per engineering, the internet or continuous current, or intermittent or continuous current, and number five, the conductor temperature. What's the temperature do you think that this conductor is going to be exposed to based on the operating area and location on the aircraft, and the installation type? Is it in a conduit? Is it in a bundle? Is it a single conductor in the free air? Meaning, does the wire just hang somewhere? Is it in a wire bundle? Is it inside of a conduit? Now, all of those things are expressed on the chart that's in front of you in some way, shape, form, or fashion. Now, I would encourage you to just go to the 8083 and then just follow the examples. It wouldn't do us a whole lot of good to talk about it over in the video format, because you have to basically trace out with your fingers where everything is. But let's just kind of notionally go through one of them. Let's say you would go through and start and say, hey, look, we have a 14 volt wire that's going to take say it's got an allowable of a zero point 0.5 voltage drop. We're gonna go 25 feet with it. So therefore we find that on the continuous circuit voltage right there, and we just go to the right. We're gonna keep on going to the right until we hit the amount of amps that we believe that it's going to carry, and we believe it's going to carry 20 amps. And so that drops us straight down and tells our wire size should be a 9 gauge wire. And so we're like, okay, cool, that's what we want. And that's all you're really doing there. You're just looking at the length of wire, the voltage drop, and the amperage. And then once you have all that information, then you just interpolate it out based on the grid. Just like any other type of grid chart that you see in these FAA manuals, you run that way. Now, I'll tell you, in real life, you basically are never going to do this unless you're in the experimental world, or which is growing, so that you may very well come across this, or you're doing something in like flight tests. Or there is the possibility that some sort of avionics modification just tells you to fabricate a wire based on these things, and it gives you a chart like this, and then you would go through there. Most all your maintenance, though, is just going to be like part number for part number. You're not going to have to fabricate just a whole lot. The machine has grown past that for the most part, and so all of aviation basically has a pretty mature supply chain that they know exactly what they want. And with certified aircraft, you can't just go willy-nilly putting on whatever you want. Now with the growth of the experimental world, you can, and so some of these old skills may start becoming more and more relevant as time goes on. If you choose to stay in the GA world, or if they grow, if Mosaic helps grow experimental into jets and everything else, who knows what could happen. But for now, for the most part, you're just simply going to replace part number for part number.
All right, to kind of conclude our review, let's talk about paralleling generators, just like why we do it, how we do it, and then we'll be done. We'll be ready to go on to turbine engine instrumentation.
Okay, so paralleling involves synchronizing two generators to work as a single power source, and they share the electrical load proportionally while maintaining a consistent voltage and frequency. So it's a pretty kind of interesting feat to be able to take two generators operated by two different engines, or even in some cases 4 engines, and getting them to synchronize up. Now, paralleling a dual generator electrical load system involves connecting those two generators so that way they can operate together to supply the power to the electrical bus or the load or wherever it's going. But while still ensuring the load's effectivity while maintaining stability. So meaning that it supplies enough power, gets everything going where it needs to go. But as things change, both with their own power generation source, or like say like the speed of the engine or whatever, and what's happening on the aircraft itself, it has to maintain that voltage plus the frequency has to match, and it has to stay in phase and in sequence. It's a pretty neat system when you think about it that way, but it creates a very solid power generation source on board the aircraft. It does this through load sharing, so the generators have to share the load proportionally based on their rating. So if you have one that's rated higher, it takes more of the load. If one's rated lower, it takes less of the load. And this is achieved through a governor control for frequency or active power and a voltage regulator adjustment. So this is where your bus tie breakers and all this stuff starts to really factor in. Um, the initial setup takes one generator is typically online supplying the load, whereas the second generator kicks on and is started and brought to the same voltage, frequency, and phase as the render. Once they've synchronized, they then start balancing the load out off the other. So once we get like one engine's cranked up and it's running and it's generating power, then the other one and it's taking everything. The other one comes online, and once we've hit on the cockpit, once you see that there's a certain NG that's been matched by both engines, and in theory both IDGs should be producing the same amount of power. Those two synchronize together, and you have uniformity across your power generation system. Now you can start to say like, okay, what we have like this appliance here, engine one's going to take it. This appliance here, engine two is going to take it. There's a little bit of extra capacity on engine one, so engine one's going to take a little bit of that, but engine two's going to take a little bit of this. And the whole time, the computer is basically just all your GCUs are simply looking at this and monitoring like what the ask is of them, and then what they can produce, and then they're closing and shutting down bus tie breakers to move the power around as needed. And it's all happening without any input from anybody. It's just simply the aircraft is just managing itself, which is super cool. However, you do have the situation where the aircraft can start kind of like doing its own thing, and then starting causing all kinds of faults. And these are the types of faults that are the most fun to troubleshoot, because they're very difficult, because there could be just a slight imbalance or something that's just slightly off somewhere, and it will manifest on the aircraft as some rando squawk, like, oh, there's squealing in the headset, or oh, there's this circuit breaker keeps popping, or whatever the thing is. And when it comes right down to it, it's like you have a GCU failure, and it'll take you a while to work your way back to those things, but they are a lot of fun to troubleshoot, in my opinion. All right, so this is the power generation map for a 737 Max, and I specifically want to call out the bus transfer system. So you can see that little green box in the kind of the upper middle. It says BPCU. That is going to be the node, which basically talks to everything and then controls the tiebreakers and moves power around as needed. So the GCUs basically say, hey, look, this is what we have. And then the BPCUs, your bus power control unit, commands those GCUs to do different things. It's like, hey, you need to produce more power, or you need to get in this phase, or you need to do one thing or the other. And then it monitors the rest of the aircraft and says, like, uh-oh, we have a problem over here. There's a bus failure. We're going to open this tiebreaker. We're going to close this tiebreaker, and we're going to start making different connections in real time to make sure that the most important things have power, and then the other things as they come into come available, they can or the power becomes available, they can start feeding it power as needed. It's a super neat and interesting system, and you have the standby power system as well. That the SPCU up top, it simply says like, hey, look, there's been a failure. The SPCU kicks in, starts like doing different things automatically, so that way power can stay online. I keep going back to Air India or did earlier in this video or another one, where the rat was deployed because both engines were come to find out ran out of gas. Well, that would have been now a little bit different on the 8.7 because just the way that an 8.7 works is a little bit more complicated than that. It's a little bit more advanced, but same concept is that like the rat was deployed because all of a sudden like both IDGs went offline and said like, hey, look, there's no more power. The GCUs were like, hey man, I can't produce anything. The BPC was like, and then it calls up the SCU and says like, hey, look, we need to do something. And then the something was like, hey, since both engines are out, we're going to deploy the rat. It's going to start generating power, and then we're going to start putting power to where everybody needs it. So that's just a real life example of this power distribution stuff and paralleling and all those good things. But that is we'll conclude our basic review. We'll be on to engine instrumentation here in just a second.